This is joint work with Yakov Lubichenko. Let me tell you a little bit about equilibria. First of all, we're going to talk about Nash equilibria, but remember, this is not just Alice and Bob playing some abstract game. This is applied more generally. Economists use it for market equilibria. City engineers use it to model traffic jams, biospheres, etc. And once players are at equilibrium, they have no incentive to deviate. That's why we call it an equilibrium. But the million-dollar question is, how do they get to this equilibrium in the first place? And it's been studied by economists for over 100 years. It's still a very debated issue. And there's also the computer scientist version of this question. So the punchline of this long line of work is, if your laptop can't find an equilibrium, if we don't have an algorithm that finds an equilibrium, it's completely unreasonable to expect the market or the players to somehow, in a distributed manner, they have their own incentives. If the algorithm that we're designing on purpose to find equilibrium is not going to reach an equilibrium, probably the players are not going to reach an equilibrium. So that means, well, maybe the solution concept is problematic. So there's been a long line of works and computational aspects of Nash equilibrium. This is just a tiny sample of those works. And after 30 years of research, we know a lot. So first of all, we know that in a two-player game, finding a 1 over n approximate Nash equilibrium is PPD hard. So I'll define what epsilon Nash equilibrium is in a second. Just for now, remember it's an additive approximation. So smaller means closer approximation. So ideally, we want to find a 0 Nash. But even if you're willing to look at 1 over n Nash, that's still PPD hard. We also know that if you have n players, finding an epsilon Nash for a constant epsilon is PPD complete. And tomorrow, those that will survive the talk today, I will show you how to show that for 2 players requires n time. So, and this is tight. So there is you can compute it in quasi-polynomial time, and I'll show you that this is necessary. So yeah, this is. I mean, we know almost everything we can possibly know about the computational complexity of Nash. Really, the computer scientist fantasy, but what can game theorists understand from these theorem statements? Under the game theorist lens. And I think that game theorists can't even read those theorems. So we have all these complexity assumptions that are necessary. And anything that we do in computational complexity, we always have complexity assumptions. And I believe all of those. I really believe that all of those assumptions are true. But even if we say, assuming p space not equal to p, then blah 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 blah. Understanding even understanding the theorem statement, understanding what does it mean for the PPD harness or ETH for PPAD. I guess ETH for PPAD, I imagine most people in this room don't even know what this means. But even a PPD harness, or if you say a p space not equal to p, it's really hard to. We have this assumption that's really hard to market it. So I think that when game theorists look at this theorems, what they see is computer scientists think that Nash hard, and this is also a theorem proved the computer scientist. So, and we're not going to get nothing that we'll do in computational complexity will do any better than this.
It's very pessimistic.
sorry. Okay. I'm sorry. Nothing in the foreseeable.
You think the
can distinguish between those assumptions and p not equal to np? I mean,
No, I'm saying even if we'd assume this under assuming p not equal to p space, you're saying, okay, I have some theorem. It's hard assuming some assumption. What are we saying? It's hard assuming that what we don't know how to do is impossible.
No, I think that they can understand statements as if they come up with an efficient way. They understand that the current algorithms they have, I don't know, Lemke-Hausen or something like this, are inefficient.
Yeah.
I think they can understand a statement, some of them, that if they have a much better algorithm for this, they can collapse the internet security. That's a statement they can understand, if it was true.
Okay, this is further is maybe practical implications of p not equal to np, but I mean I think as a math theorem it's still problematic, and again I love computational complexity. This is what I do most of the time, but I think it's nice that if we're talking about communication complexity, we can actually have a theorem that we can prove, and even a very simple statement that I'll show you in half a slide. So this is the entire setup. Each player knows their own utility function, their own utility matrix, and we'll prove lower bound how much communication they need in order to reach an approximate equilibrium. Okay, so if we have two player and each player has n actions, well, they each have an n by n matrix. They can, with polynomial and n communication, they can just send their entire matrix. But a lot of time, this n is really exponential in the dimension for many applications, and we would like to do this in less than polynomial communication. And we show this is impossible. You actually need polynomial communication, even for epsilon Nash, for constant epsilon. And for n player game, where each player has two actions, we actually get exponential in the number of players.
So is epsilon, is it true for every constant epsilon?
No, for some constant epsilon.
Both statements?
Yeah.
What's known for every constant?
I know that for two player there is some constant 0.4 something where they actually get polylog communication.
Is there any notion of smooth analysis, or like for a noisy, if you have some noise to the valuations?
So this paper already proved that even for two-player, if you had at least they proved that smooth Nash is already hard, Chen Tang. So even for two-player, I mean, in the computational
so the hard instances are stable. If you
yeah, and these I think there are with at least for the smaller approximation factor there. I think for all of them there are without loss of generality, like almost like 0-1 instances or something. Oh. Yeah, by the way, I forgot to dress up for Halloween, but SpongeBob is celebrating. More questions about the...
It's hard for me to understand the relation between the previous slide and this slide.
Okay, so sorry, so
powerful, it gives you a
no.
conditional lower bounds, which is better.
Yeah. Okay, but this is for a setting where the input size is exponential, right? I mean, otherwise there is no communication complexity.
Okay, so in the previous thing, you assume that the matrix, like you want to compute in time relative to the size of the matrix, and here.
Okay, so compared to computational complexity. So where was I? Right. So. Okay, so in the two-player, right, we're saying even if you want, here we're saying communication complexity is at least polynomial. We're saying computational complexity is even worse than polynomial, right? It's quasi-polynomial for two players, or actually exponential if you want a better approximation. And then this result is for a very natural class of succinct games. So there is a succinct representation but for a general game, it doesn't even make sense to talk about computational complexity. Or you can talk about it, but it's different.
Small and then big N, small N in the first theorem and big N in the last theorem. Same?
You should think as little n as you
Yeah. Sorry. This should be capital N. You're right.
Well, if you have little n players, then little n is not really, or it's not clearly how it's related to the input side.
Yeah, so you need a succinct representation of this.
Yeah. So this result holds for a succinct representation, and for general game you have exponential size representation, and then it's the you actually get communication complexity. This theorem.
There is a reason you say that typically this capital N is exponential. Is this true?
So I don't want to say typical, but for some concrete applications, it is true. For example, if you have auctions and you're bidding on items, and you can want subsets of the items, and there are some concrete applications where this comes out as like exponential.
And you're going to these results, or just?
I was mostly going to tell you about the proof, but if I mean,
no, just there was some work on this.
Are you talking about the Rough Garden Weinstein?
Yeah.
Okay, yeah. I don't have it on the slides, but I'll briefly mention how it relates. Okay. Oh no, I have to do that very carefully. I'm on video, so.
On video, yeah. We
on camera, yeah.
Against you, it's
the Tim and Omir are going to see this, and I'll be in trouble. Okay, let me actually define the epsilon Nash briefly. So Nash equilibrium simply means that every player is playing optimally given best response given what everyone else is doing. So if no one else is changing, they don't want to change either. Epsilon Nash equilibrium means that every player is playing epsilon optimally, so they can gain at most epsilon from deviating. And recently we defined an even more relaxed solution concept called epsilon delta weak Nash, where I'm only requiring that most players play epsilon optimally. Only one must delta fraction. Okay, so we had this catchy tough. Can almost everyone be almost happy?
But it's not about happiness, it's about stability. Why would this be a reasonable solution concept? I mean, epsilon Nash, one can believe that maybe the evaluations are a bit noisy and epsilon could be trouble.
Okay.
Why should 1% of the players decide to...
Excellent, and I had to convince Christos about this. He gave me the same hard time when I told him about this question. So the short answer is if you only have a small fraction of your players unhappy with the current solution, you send someone with a big baseball bat to their house and make sure they're happy with it. A more peaceful way of looking at this is that you're just changing your utility function, exactly. You're only slightly changing the utility function. A more peaceful way of looking at this is, like I said, it's not just Nash equilibrium. There are many market equilibrium, etc. And this turns out to be, if you have by itself, if you have if most of your players are approximately equilibrium, relates to, like, you can ask similar questions for market equilibrium. So most products are approximately market clearing, but you only have a few products that are sold for the wrong price or something like that. And finally, this relates to the computational version of this question. It relates to a really nice question of PCP for a PPAD. So this is just, we have a constraint for every player, and now you want to satisfy 1 minus delta of the constraints. So it's interesting. It's interesting by itself for theoretical computational reasons. But here I'm just going to tell you that the communication complexity of epsilon delta is still exponential. even if you're doing this most relaxed notion. Let me tell you a little bit about why this result was some of the obstacles that we have to overcome in this proof. And the first one, and that happens in all of Nash equilibrium problems, is totality. So there always exists an equilibrium. And this is a problem. It makes working with diffusion problems a little trickier, but also means that there always exists an equilibrium. And I can't just say, oh, the instance doesn't have an equilibrium. There always exists one. I have to hide it. That was kind of hand wavy, but we'll see more later. And the second thing is there always exists a small support equilibrium. So if you want epsilon Nash, there exists in two players. There exists an equilibrium with support log n over epsilon squared. So I think the epsilon should be out of the log. So this means that for communication complexity, there exists a non-deterministic protocol that runs in polylog communication. And as some of you know, in communication complexity, unlike computational complexity, most harness proofs, most reductions actually start from set disjointness or something like that. That's hard also in the non-deterministic case. And there are very few examples of separations between deterministic and undeterministic. And maybe Avi will correct me on this, but I think it's fair to say this is the first natural application where the deterministic and non-deterministic have an exponential separation or randomized.
It's a very different thing, right? I mean, in communication complexity, actually, if you have non-deterministic quick protocols in both directions, 0 and 1, then you have a short deterministic protocol. We have NP intersect co-NP equal P in communication complexity. This is a different type of problem, where it's a search problem, and so I don't think that it was studied that much.
No, it was, and there are known examples, but I think this is one of the first maybe natural example where this phenomenon happens, and it's many of the techniques don't apply because of this issue.
I think that's true. I'm saying that the type of problems most studied in communication complexity are Boolean functions. And for Boolean functions, you cannot have an equilibrium between non-deterministic and deterministic. It's always
one of them.
No, for one of them is exactly. But if you have for both of them, this is sort of for both, right? I mean, the way Aviad talks about non-deterministic is that
for the decision, you can't prove that there isn't a better equilibrium.
No, exactly. Yes, it's a different
kind of problem.
Yeah. But yeah. For now, we don't have to talk about decision at all. You can just there always exists an equilibrium. You can find it, and if you have a witness, then you can find it efficiently. But
So is it for randomized or deterministic?
our lower bounds hold for randomized. I'll get back to that later. But all the lower bounds hold for randomized.
Actually, a separate question. So does this lower bound also hold, the support size lower bound also hold for zero-sum games? I care about it for some other reason.
Okay, so this is an upper bound of the support size. But
that's
but there's also matching lower bound.
Of zero-sum games?
Yeah, also for zero-sum games.
Okay.
Yeah.
Any reference?
I'll talk for 94. You can look at and this is why for the computational complexity of two-player Nash equilibrium, for the same reason, there is a quasi-polynomial time algorithm, and that's why the lower bound I'll show you tomorrow is tight. Okay, let me give you an outline of the proofs.
All the first statement, the two-player.
So I'll prove the first statement of two-player, and the second statement is it follows from the same idea with some extra stuff. So these will be sort of the players. I'll tell you what all of these mean, but I'll just briefly mention that maybe part of the novelty in the reduction is the direction of the arrows between all those things. So we can go from end of line to a simulation theorem and to Brouwer point. I'll tell you what this means later. But the Brouwer fixed point problem and the simulation theorem don't really work well together. So the Brouwer is really inherently continuous, a continuous problem, whereas the simulation theorems are very discrete. And the paper you asked about earlier about the Roughgarden and Weinstein from recent Fox, they sort of tried to go to Brouwer and then hop to simulation and then to Nash, but something breaks along the way and it doesn't quite work.
But can you remind us of the result?
So the result, they don't have results for Nash equilibrium. They have a result for some version of the communication problem of a Brouwer, finding a Brouwer fixed point. There was no result for Nash equilibrium, and yeah, maybe I can say more offline. But I mean, they sort of had all the ingredients, just connecting them is the. Okay, so the first thing I'll tell you about is this n of a line problem. So the input of the problem is a graph. You should think of it as an exponential size graph. For every vertex, I have the in degree and out degree are at most 1. And I'm giving a special vertex 0 that has in degree 0 and out degree 1. So it has an odd degree total. And I'm looking for some other vertex with an odd degree. And by a parity argument, there has to be exist such other vertex. And briefly, the computational problem I told you about earlier, this class PPAD, is when I'm giving you the graph implicitly by poly-size circuits that tell you for each vertex what are the next and previous, the incoming and outgoing edges. And the goal again is to find such a vertex V, and PPAD is a class problems are reducible to or from. I'll think about it later. To this problem.
So you want output without degree or with out degree 0?
I want odd degree. So this is also okay. And for in computational complexity, we conjecture that you need exponential time, but query complexity, it's actually relatively easy to prove that you actually need exponential time, actually omega of 2 to the n. Questions? Awesome. Okay, so we want to get to communication complexity. That's what we're after. So let me tell you about how you one way to phrase the n of a line as a communication problem. So I'm going to color all the edges. I'm going to blue or red independently random. And I'll give the blue edges to Alice, and I'll give the red edges to Bob. And I'll let them try to solve this problem, right? So again, the query complexity is exponential. And because what can you do, right? You just get a vertex. You can just query the next vertex until you get to the actual endpoint. You can't see anything. And for Bob, this edge, the one that leads to this endpoint, looks just like any of the other edges. Naively, you might think, at least I was sure this would also be a exponential communication complexity, but there is actually a very efficient communication protocol for this problem. So they're just going to sum up.
How do you divide the...
Randomly. I'll partition the edges randomly.
So they're...
Every edge either goes to Alice or to Bob.
backward edges?
let's forget about.
Yeah,
Yeah,
the-
you get the direction, right?
same direction.
You get the direction. When I give you an edge, I'll also give you the direction. There is an edge from U to V.
Okay, it's just in this picture it goes forward, but it can go back.
So okay, so I'm cheating a little bit. This is the restricted version when I only have one line. But so everything I'm going to tell you on this slide actually works for the more general. Does that answer your question? Sort of.
You can permute the names of the services.
Yeah, just he wrote it the same way as forums.
Okay. So let me tell you a very silly protocol that is super efficient. You get exponential savings from query communication. Each of Alice and Bob just sum up the endpoints of the edges that they have, and V is the only one that's going to appear once. You say it's 0. So when they subtract or they sum modulo 2, V just comes out. So this is a much more efficient way than just querying vertex by vertex. The point of the slide is to show you that communication can be sometimes much more efficient than query complexity. This doesn't work. Nevertheless, we have those miraculous simulation theorems that tell us how to partition the inputs, how to distribute the inputs in a way that makes communication hard. So for each bit in the input, I'm going to give Alice a vector alpha of b, and I'm going to give Bob a vector beta b, and the guarantee is that I'm going to give Bob an index of beta b, and the guarantee is that if you access Alice's vector at the Bob's index, you actually get the bit in the input. So instead of querying, you can Bob and Alice can simulate any query complexity.
So this is
query protocol.
Like the inputs were the edges in the.
So you okay so you can do this for you do this in general for every bit in the input. So so in the query version, what I'm querying is the query is I give you a vertex and you tell me what's the next what's the predecessor and successor. So the bits really there are a few for every vertex I have to give you a few bits, but so you can actually look at the restricted case. The graph is a constant degree expander, and then you only need a constant number of bits for every vertex.
So literally each bit in this description is given by this.
Yeah. Okay, so and if you're doing this, if you're distributing the inputs with this according to this in this manner, then we have this amazing theorem which says that if you're doing deterministic communication and deterministic query, the deterministic communication complexity is greater than the deterministic query complexity. This is the standard notation. This is P is the standard P from polynomial time, and DT is decision tree, and CC is communication complexity.
So it's a lifting theorem.
Exactly. Simulation theorem, lifting theorem, same thing.
And who is the RM?
Raz and McKinsey.
No, that's why.
Okay, yeah. And there's a generalization by Goose. Unfortunately, for randomized communication, we don't have a simulation theorem. So the first time we posted this paper in arXiv, we actually had only a lower bound for deterministic communication. but it turns out there is this WAP class I'll tell you about in a second, and Mika Goose kindly told us that we should use it and how to use it, etc. So now we actually get the lower bound for randomized communication, because WAP is stronger than randomized. I'll tell you in a second.
So at least for the total functions, all of them are related, but maybe no functions are not. I mean, like if you don't care about like a polynomial factor, then you could get something. But this
In
is
the
really
query
about
in the query model.
what?
In the
The
query
query
model.
model. Yeah, I'm saying
Yeah.
that you can leave some other notion that is weaker, which is only polynomially related to the to BVP. If you don't care about getting the exact.
Oh yeah. So I mean we're lifting this WAP and
the WAP is polynomially related to the BVP.
we'll just prove a query complexity lower bound for WAP.
Okay.
Yeah, does that answer the question? Okay, so maybe I ask after the next slide, and if it's still there, ask after the next slide. Okay, but keep asking questions, please.
Don't even penalize you for the time.
I have like half an hour worth of slides, so ask. We're almost done, so ask more. Okay, so let me tell you what this crazy class WAP is. So it stands for weak almost wide PP, which I'll be honest with you, I don't know what this means. This WAP is actually very crucially defined for a decision problem. So let me do a decision version of this n-of-a-line problem, where I just want you to output accept if the first bit of this vertex v is 1, reject if it's 0. And I can I can restrict the case where for all the different, even if you have more than one v, they will all have the same first bit, so it's okay. This is something we cannot do in the computational complexity world, because we don't have the hard instance. We can say even this instance is hard. Okay, now the definition of WAP says that for some alpha which can depend on n, can be exponentially small in n, in the completeness, if it's a yes instance, I require you to accept with probability between that's almost alpha or at most alpha, in that range. And in the soundness, you may accept with probability at most epsilon alpha. So first, let me show you the this restricted case that we had earlier, when there's just one line, this the query complexity of the WAP query complexity is actually very small. So here's a protocol. I'm going to guess v, and accept if and only if this is actually an n-of-a-line, and the first bit is 1. So for alpha 2 to the minus n, I actually get the accept with probability exact 2 to the minus n if it's a yes instance, and I never accept it if it's a no instance. So if there's only one line, then you're doomed.
So guess is pick at random.
Yeah. Oh, I should just say that you already see this is, you can see from the definition, this is stronger than BPP. BPP I force alpha 1, right? The standard randomized complexity that we're used to. Okay, so here's the actual hard distribution. I'm going to choose a random from one of the following 3 distributions. First, maybe I just do one line and it ends with a 0. Or I can do just one permutation of all the vertices and it ends with a 1. And we saw this is not enough, so we add a third distribution, which is I'm going to have 2 lines, break to random lines, and they both end with a 1. And the second line also needs to start with a 1. And now the acceptance probability of, so if we're trying to do the same trick as we did earlier, right, where we are guessing a vertex, and if it's n of a line, and then we and it's 1, then we accept. The acceptance probability on this distribution should be twice the acceptance on this one. So it's going to violate the upper bound and the acceptance in case of completeness. More questions about WAP?
Yeah, why,
Is this weaker than non-deterministic?
So how does it relate to non-deterministic? I think it's incomparable. So if I didn't have this upper bound on the acceptance probability in case of completeness, then you'd get like I think almost like Marilyn Arthur. I'm not sure, but there's this weird restriction where even if it's a yes instance, you're not allowed to accept too much.
It's weird.
Yeah.
It's really weird.
but what's the value of the lifting theorem for this model? I mean, at the end, you want just to prove that it's
Okay, so
randomized communication.
yeah, so this is strictly stronger than randomized because right for the specific case of alpha equals 1, you get the standard randomized communication.
Oh, I see. And when the reduction, the lifting theorem preserves the alpha, or
No, it changes it. But it says that if there for any alpha you could do 1, you can do that. There is some alpha you can do that. It also doesn't preserve epsilon, but it goes from constant to constant.
So anyway, the communication version is a lower bound of the randomized communication. This is what
Yeah, so I'm saying if the communication WAP is the lower bound of the standard randomized WAP, standard randomized communication. Okay, so we went from N of a line. We have the simulation theorem that says that even in the stronger WAP model, communication complexity is exponential of this simulation N of a line problem. Now let me tell you about this Brouwer problem is Brouwer's theorem says if you have a function from continuous Lipschitz function from continuous functions from compact domain to the same domain, then there exists an x such that f of x equals x. There exists a fixed point, and we want to find such an x. Okay, so this is a construction. I'll hand wave a little bit about it. If you want, I'll tell you more about it tomorrow in the longer talk. So this is a classic construction from the 80s, and the arrows in this construction. So think of this as a shot of the hypercube, and the arrows in the construction are the displacement. So f of x minus x, and everything that's interesting is happening in here. I'll tell you about this in a second. But everywhere else, we have the special direction, which is up. And everything is pointing up, and then when you're really at the top, you're going towards this special point, and from here actually going down. And here we'll embed the path that we get from the N of a line instance. And this slice is like a 2 to the end. It's like an n-dimensional thing where we can embed things in the subcubes correspond to the 2 to the n vertices.
But it's exponentially smaller than the whole.
It's exponentially smaller, and you know that everything is here, but still, actually, no. This is in the final construction it will be exponentially smaller. Right now, it's not even exponentially smaller. But okay, so the path. So we'll have this like path that goes along the path defined by this N of a line, but now we have to define the displacement so that we never have a fixed point except at the very end of the line. So it turns out the way to define the displacement is this, and this is what happens when the path goes into the wall.
We Aviad, you have to explain what you're doing here. This is part of the reduction.
Okay, yeah. So, sorry, yeah. So I want to reduce n of a line to Brouwers. I want to say that if finding the n of a line is hard, then also finding a fixed point of a continuous function is hard. Okay, so this is our goal, right? So finding a continuous function, the fixed point of the continuous function is as hard as finding this n of a line. And so I'm actually constructing this function, given this instance of this graph. And I'm hand waving a little bit about the construction. I don't have a better way to explain it other than show you the equations. Okay. So I'm explaining. I'm actually showing you what this f looks like, what the displacement is. So everywhere the f just sends you to the special point where I'm actually embedding the path along the path of I get from the graph. And now to ensure that you never have a fixed point, okay? So here's how we never get a fixed point except at the end of the path. So suppose that we have an edge that's pointing towards into the wall. So here the center will have the displacement pointing into the wall, like in the direction of the path. Slightly outside we're pointing towards the path. And slightly further outside, we're pointing against the path. But because here it's when I'm pointing in this like towards the path, and here I'm against the path, these are orthogonal. I don't have cancellation, so I can interpolate. And further outside, I'm pointing in the special direction, which was up in the first picture. And the most important thing you need to remember about all of this is that I always have this default displacement that I can always point up, and that's always like a safe direction to point, except when I'm actually at the path, when I actually know what's going on.
So what do we really need to understand? This is a black box, or this internal construction will be used in what you're going to say now?
I'll tell you in a second what you need to remember. Okay.
You also have to remind us. So this is Papadimitriou, right?
Yeah. Okay. Sorry. So this is Hirsch, Papadimitriou, and Vavassis. It's their construction from '89.
And this was also used in the rough garden Rubinstein.
Yeah. So they try to use it as a black box, and we need slightly more stronger on this. But first we'll strengthen it, and then we'll also use some properties. Okay. Okay. So the theorem says that if you have this like n of a line instance, you can embed it as a Brouwer fixed point function, Brouwer fixed point problem, where finding an x that in infinity norm is epsilon approximate fixed point is as hard as finding the n of a line or n of a line. In this paper that I'm going to tell you about tomorrow, we actually strengthen this to like two norms. So this is think of as a normalized two norms. So there is some you divide by n or root n or something. But the idea here is now that in a constant fraction of the coordinates, you're a constant far from a fixed point, and you see this is essentially what you need both for this epsilon delta weak Nash, and also to get to actually two players, you need this two norm. And other than the fact that finding a Brouwer fixed point is hard, though, one thing you need to know about this function is, like I said, for most of the points in the hypercube, I have the same default displacement, just pointing up. So it means that if I don't know what's going on, if I can't, and this construction uses error correcting code, etc. If I don't know what's going on, if I'm at a point where it's not clear what's the how to round it and decode it as a vertex of the graph, if it's not clear what's going on, then I'm just safe to just point up. Except and only in those few points where I can actually decode, then I can actually know which direction the path is going, and I can do this locally, etc. Okay, so we know that communication complexity of n of a line is hard, And we know that finding a Brouwer fixed point is as hard as finding an affine.
In the
So
season.
can you explain again how you got the 2 norm here? What
Yeah.
did
Okay. Yeah. Sorry. I was super fast here. So in the original construction, in this HV construction, sorry, there's a missing step here, but you think of them as you're encoding for every vertex corresponds to, you can think of every vertex as corresponding to a subcube of the hypercube. So think of the if I'm going from the vertex 001 to 000 to 001, then maybe I'm going right one in one direction, and then maybe I'm going up in one direction, etc.
This is how you embed this path.
Yeah, this is the original embedding, right?
Hypercube.
Yeah, this is how I embed the graph as a function on the hypercube. There is some path that's going from neighboring subcubes.
So the graph is just a path in the hypercube,
Yeah,
and the arrows tell you.
the arrows tell you how to actually implement as a continuous function.
But it's not clear where you put the graph, right?
Okay, yeah. So
When you fill out the vertices,
if I write on this, can you see anything or?
Yeah.
Push B on the here.
Sorry?
Press B.
B? Ah, wow. Okay. Thanks.
so right, this is the main difference between like your work to the team and Omrivo?
No. So I should. So like that gets better parameters, but even without this, we would get harness for Nash, which theirs doesn't.
Oh, okay.
Theirs doesn't say anything about Nash. But their theorem doesn't say anything about Nash, whereas ours doesn't, and that's not the.
Oh, this is
This just allows us to get actually epsilon as for constant epsilon for 2 players, whereas if we use the original Hirschman and Vavasis, we would get like 1 over polylog for for 2 players, and we get epsilon as for many players instead of epsilon delta for. Okay, so
not it.
It's not it.
yeah. So
You're
you
still
don't care. Okay.
explaining.
I wanna know
You
it.
can still explain.
Okay. What's that? Okay. What's that?
Yeah, I wanted to know what's it.
What's it? Okay. Let me get into the 8, and then we can go back either today or tomorrow. Because it's more relevant to tomorrow's talk. If I press B again, wow. Okay. So this difference just gets better parameters. I'll show you later how much better. But and it's completely crucial for tomorrow. But the first step of the it is not looking at this construction as black box. And in particular, you notice that noticing this observation, that for most points, unless we know exactly what's going on, we can do this go up thing. Okay, and I'll hand wave how that fits in later. Okay, so we know this simulation theorem that again Tim and Omri also knew, and we know this Brouwer function that up to this difference again Tim and Omri also knew, and the question is how do we put those together? And we are going to, instead of going from one to the other, we're going to put them together in one game gadget, and that's the it, and I'll tell you about that
So
now.
just to clarify, when you have query Brouwers, query fixed point, there's
Yeah.
a Lipschitz condition, and when
Yeah. I'm sorry. So f is a Lipschitz function.
and that's a problem?
Okay. Sorry. So f is going to be a Lipschitz function for and in the HPV it's Lipschitz in an infinity norm. Here it's going to be Lipschitz in 2 norm, but and there it's going to be Lipschitz in the Lipschitz constant depends on epsilon, but it does not depend on the grid that I'm looking at. Okay, so you can look at the arbitrarily small grid, and that's sort of part of what goes wrong in the other paper. The Lipschitz constant here is independent of the grid. You can make the grid arbitrarily small and keep the same Lipschitz constant. because there is some underlying. The grid is just there to talk about finite things, but there is some underlying actual underlying continuous function. Okay.
So if you try to work with the continuous function and lift it, then the lifting.
But the lifting thing, it gives you something that's discrete. This is a continuous function, and the lifting gadget, right? This like you get Alice gets an array and Bob gets an index to the array. That's something discrete.
And you can smooth it somehow.
I mean, Tim and me tried really hard, and that's where. Okay. So let me tell you how to get around this. The fact that we went here and went here, now we want to combine both in a single game. Okay, so there's this sort of standard thing, at least by now, in this equilibrium computation thing. It's called this. This is essentially a mutation game. Maybe I'm cheating a little bit, but the idea is that Alice is a utility. Oh, sorry. So Alice's strategy. She picks a vector in the continuous hypercube x, and Bob's picks a y, and you can discretize it later, and everything is safe. Okay, but for now, let's think of them as continuous strategies. So Alice's utility when she picks x and Bob picks y is the difference, 2 norm of the difference between x and y. And Bob's utility is so Alex wants x to be as close to y as possible. Bob wants y to be as close as possible to f of x. Okay, and the nice thing about working with this 2 norm squared is that in general we have mixed strategies, and they're really hard to reason about. But when you're using this, if you're taking expectation over Bob's y's, you get the difference between x and the expected y, and the variance of y. And the variance of y doesn't depend on what Alice does. So you can completely ignore it, and now x just tries to imitate the expectation of y, and you can forget about the fact that there is a mixed strategy and so on. You can only talk about pure equilibria. At least until you discretize the space. Okay? So now it's proved that in every equilibrium x is equal to y, and it's equal to f of x. Questions so far?
So what is this doing? You take one game and you transform it to be.
No. I'm just. This is the game. This is the game, without this line. So the first line that defines the game.
Okay.
Okay. And I'm telling you the. No new game.
For which you want to find an epsilon Nash, and this is supposed to be hard.
Yeah, this is exactly. Thanks, Avi. This is a hard game. Okay.
Oh, okay.
I'm saying you an interesting property about this game is that in general Bob may use a mixed strategy, but when we're analyzing this game, we don't need to think about Bob using a mixed strategy because of this property that there is this variance of y term which is additive for Alice, so Alice can't affect it. She doesn't care about this. And then Alice's utility depends essentially only on an expectation of y.
So do you want to write the same equation for both, right?
So yeah, and the same thing holds for Bob. Yeah. So this is wonderful, and we're almost done, except that we cheated.
So it means also this is unique.
If there is a unique fixed point, then you have a unique pure equilibrium. If there are multiple fixed points, then each of them has.
So sorry, this is a family of games.
Yeah.
Right. If you give me an
F, yeah, then you can define this game.
and they have this nice property.
Yeah.
At
Uh-huh.
equilibria, you can play.
So any equilibrium is a fixed point, and fixed point is an equilibrium.
Strategies, and now you're gonna show us that it's hard to find an equilibrium. Or
So we already know the it's hard to find a fixed point.
not.
It's you fix the fix.
Communication.
Yeah.
Communication is
Okay. So Okay, so okay, you're almost there. So I'm cheating a little bit, and that's almost where I'm cheating. I mean, this in the query complexity, this is the reduction. Okay. But for communication, I'm cheating because here f appears in Bob's utility function. But in the communication problem, I'm not allowed to just give Bob the function, right? Because I have to somehow distribute the inputs between Alice and Bob.
Because then Bob will be able to compute.
Yeah, but Bob knows everything. So in this game, Bob knows everything, and he can just compute the equilibrium offline.
So Bob can't compute his utility.
But no, I mean the communication game that's fixed. The communication, the rules of communication are Bob knows his own utility. So this is So this is not exactly. So Bob can. Okay, so I have to do something different. Okay.
So you leave that maybe to win
Okay,
them.
let me show you.
Able to compute.
Okay, I've spent a while thinking about this problem, and several other people have, and in hindsight it's embarrassingly simple, but only in hindsight. So okay, this is the simulation game. Now each of Alice and Bob are going to have besides this X and Y that they pick, they're going to pick some other as their strategies are going to tell us some other stuff. Okay. So first, as before, we really liked this part. The Alice wants X to be as close to Y as possible. Now Bob, he sees. I mean, given Alice's X, Bob wants to decode X as a vertex of the n of a line problem. And so if the point in the hypercube actually really looks like a vertex that you can decode, etc., then Bob really wants to say what this vertex is. And if it doesn't, then it doesn't matter what Bob says. We can just point up in the. Okay. So once Bob decodes this X as a vertex, we also incentivize Bob to tell us what he knows about this vertex. So what is the beta, the index to this in the simulation, in the lifting theorem. Okay, so he has to tell us this beta for this specific vertex that he decodes from Alice's strategy. You remember the simulation theorem for every vertex? I have some input and I gave Alice a vector alpha and Bob an index beta. And Bob wants to output this. We incentivize Bob to output the right beta. And now Alice, given that Bob said some vertex and has some and gave some beta, she wants to output the right alpha for this vertex and beta.
These are payoffs, these ones.
Yeah. So it's
otherwise
zero. Yeah, 1 and otherwise 0.
Where is F here?
Thanks. So here's F. Okay, so given Alice's X and given what she says about alpha, Bob can locally compute F. He can locally compute the next and previous vertex of this n of a line graph, and he can say what the displacement of F is at this specific X. So given what Alice says about given using Alice's alpha, Bob can locally compute f of x, assuming that what Alice said is true, is the right alpha.
So now 2f's.
So Bob knows the general structure of f, which you also know, right? Bob knows that f looks something like this, like these two pictures, right? But to actually know in which direction everything goes in here, he needs to know the edges of the graph.
Alpha of beta is just 1 bit, and these are many directions.
Okay, so yeah, for each vertex alpha and beta, it's going to be really a few bits. I'm making it simpler. It's a constant number of bits, and that's enough because we're working with an expander. And that actually tells you the previous and. So this is it.
And we should add up the payoffs. There are several.
Yeah. They just add up the payoffs. And it's not hard to tell if in any approximate equilibrium, Alice and Bob, both of these actually they get the one. Like all of these conditions hold. So like Bob says the right rounds to the right vertex and outputs the correct beta, and Alice outputs the correct alpha. So Bob is correctly locally computing F.
In case you're wondering, I'll ask many more questions offline.
Oh, okay. Great. Anyone on this side of the room wants to ask a question? I'm sorry. I keep getting the questions this side. And I feel like I'm turning.
We thought we point a pain in the neck.
Okay, so I'll wrap up and then Gilad can ask me more questions offline.
We get online questions offline.
Oh, awesome. Yeah, so this is it. Let me just up to all the lies I told you. This is it. Yeah, so Avi, you're right. I didn't tell you anything about this n-player game. So in the n-player, it's just every player plays a coordinate, one of the coordinates in x and y.
It's a reduction. It seems like you can embed many coordinates into one. If you want. You have exponentially many strategies per player in the two-player game, and now every player will be like n little players. So it's two strategies.
Close, yeah. Essentially, it's close. You have to make sure the utilities are aligned and everything, but everything works. So just mention this. There were all these query complexity lower bound, and this kind of subsumes everything. And some economists are interested in this uncoupled dynamics. They're saying, okay, each player knows their own utility. Now they're playing maybe sort of a repeated game, and they're updating. They're doing some kind of learning, and they're somehow updating their mixed strategy. And there's a question of how can this converge to an equilibrium? You know, this says exactly that it takes really long, because communication is a sort of equivalent to just communicating with those mixed strategies in each playing a different action in each turn. Thanks, and come to my longer PCPH talk tomorrow.